Pluto is a far-off and unusual bantam planet that was once a member of our planetary gatherings family. Regardless, late astounding statements by leading astrophysicist Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with an amazing revelation. They suggest that this cold world is on a possible collision course with Neptune. However, how could this occur, and what might be the consequences of such a colossal event? Are we witnessing a remarkable cosmic quirk, or is there more to this impending epic mishap? Join us as we explore the possible outcomes of a Pluto-Neptune collision. Pluto, once considered a planet, but later reclassified as a dwarf planet due to its unusual orbit, remains a subject of interest in the vast neighborhood of space. According to recent assumptions by leading scientists, Pluto's trajectory is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku have raised the alarm about a potential collision between these two planets, which could pose a significant risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full cycle. However, the intrigue doesn't stop there. Pluto's path is marked by its highly eccentric, elongated shape, straying far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, tilted at 17 degrees to the ecliptic plane. This inclined and eccentric nature adds layers of unpredictability to its orbital model. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, contradicting what we might expect from their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The examination of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its unique trajectory. Unlike other planets whose orbits lie close to the ecliptic plane, Pluto's path stood out with its significant inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amid these complexities is a testament to the intricacies of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem illustrates how its path, Neptune's path, and the Sun's gravity all interact. The terms alpha libration and longitude libration, along with the VZK effect, are significant in this context. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the case of Pluto and Neptune, this term indicates that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is key in preventing their paths from colliding. Longitude libration, on the other hand, refers to the up and down movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is positioned well above their orbital plane, providing an extra layer of protection from potential collisions. Another crucial factor is the VZK effect, named after three researchers, von Zeipel, Kozai, and Litov, who studied how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational interaction affects how they move. In Pluto's case, the VZK effect helps explain why its orbit around the Sun is so eccentric. Despite Pluto's orbit appearing to be erratic, this effect helps keep it moving smoothly over time. Understanding its orbit is essential, as it gives us a clearer picture of the solar system's dynamic nature. The position of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also underscores the importance of ongoing observation and study of these irregularities to better understand our place in the universe. Exploring the depths of space often leads us to confront the unusual behavior of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital bifurcation, which refers to the delicate dependence of a celestial body's path on its initial conditions, is particularly evident in Pluto's case. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term trajectory. In the vast realm of our solar system, Pluto occupies a unique spot that challenges our understanding of planetary order and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant findings about its stability and behavior. One of the most intriguing features of Pluto is its surface, which is a complex blend of ice, rock, and various compounds. The New Horizons spacecraft, which flew by Pluto in July 2015, provided unprecedented data about this distant world. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of the most remarkable features is the Sputnik planitia, a large heart-shaped plain primarily composed of nitrogen ice. This region exhibits a diverse array of geological features, including massive ice sheets and what appear to be flowing glaciers. The presence of these features suggests that Pluto might still be geologically active, despite its great distance from the Sun and low temperatures. Another fascinating aspect of Pluto is its atmosphere, primarily composed of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is thin, yet it shows intriguing seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This unique behavior reflects the intricate interaction between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze onto the surface, while, as it moves farther away, these gases can sublimate back into the atmosphere. The relationship between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space that lies between them, rather than Pluto merely orbiting Charon. This unusual relationship contributes to the gravitational dynamics of the region, affecting the orbits of other objects in the Kuiper belt. The Kuiper belt, a region beyond Neptune populated with small, icy bodies, is home to many other dwarf planets and potential impactors. This belt serves as a reservoir of ancient material from the early solar system, giving scientists a glimpse into its evolution. Pluto's orbital characteristics could offer insights into the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a crucial role in shaping their current orbits.